Video is about geometric transformations of complex numbers. I'm going to start again by looking at the real number line just for a moment and talking about that first, and then we'll continue on to look at the Argand diagram and complex numbers. So here I have a real number line, and I'm going to select a variable on that number line. I'm going to say that x is equal to 1. I'm using x now because I'm dealing with real numbers. Z I'm going to save for complex numbers. So I'm going to mark that x on the number line. There it is at 1. Now I want to multiply x by 3. So I'm multiplying 1 by 3, which is obviously 3. So that's my calculation, but what's actually happening on the number line? Well, if you think about 1 is a distance of, at the risk of stating the obvious, 1 away from 0. If I multiply it by 3, what I'm really doing is I am changing its distance from the origin by a factor of 3. So when I multiply by 3, then visually what I'm doing is I'm drawing a line that is 3 times as long from the origin. And that lands me at 3. So I've taken my distance, or my modulus if you like, and I have multiplied it by the factor that I wanted to multiply by. If I started off at -1 and I wanted to do the same thing, so I'm at -1 and I want to multiply it by 3, so in this case I'm going to say that 3x equals to -1 by 3, and I get -3, then I have looked at the distance from the origin, or from 0 to -1, and I have multiplied it by 3. But notice that in each case here, direction has been preserved. So when I was multiplying 1 by 3, I kept going out in the same direction, the positive direction. When I was multiplying -1 by 3, I kept going in the negative direction. So we'll see that happening as well when we're dealing with complex numbers in a moment. These values that I'm multiplying by here, they're obviously real number values that I'm multiplying, but they can also be called scalars. And the reason they're called scalars is because they scale the position of the number on, in this case, the number line. So when you scale something, you multiply it by a factor. So let's have a look at how this might apply then to the Argand diagram. So I'm going to look at the case of the complex number z1, which is 1 plus 1i. I want to graph this on my Argand diagram. So it's the point 1, 1, and I'm going to mark it in. So there's my z1. I'm going to just draw in my modulus because that can frequently be a useful thing to note in any Argand diagram. And now I want to multiply z1 by a scalar, so by a real number. So I'm going to say, for example, that I want to find 4 times z1. Well, if I was to do this algebraically, I'd simply multiply z1 by 4, and that would give me 4 plus 4i, or the point 44. I can mark this on my Argand diagram also. So there it is, 4z1. Just notice visually that if I was to draw the modulus of 4z1, it's actually 4 times as long as the modulus of z1. So in effect, by multiplying the complex number by a scalar, I've pushed it 4 times the distance out from the origin. And I can calculate the modulus of z1 and 4z1 to confirm that fact. So the modulus of z1 is going to be the square root of 1 squared plus 1 squared, which is root 2. And the modulus of 4 times z1 is going to be the square root of 4 squared plus 4 squared, which is root 32, which of course can be written as 4 root 2. So you can see that the modulus of 4 times z1 is 4 times as big as the modulus of z1. So here we have a fresh Argand diagram, and we're still looking at multiplying by a scalar, but with a bit of a different focus this time. We're going to say that z2 in this case is going to be minus 2 plus 1i. And I want to identify where that is first of all on the argand diagram. So I'll write it as a point, minus 2, 1, and I'll plot it in. So there's my Z2 point. I'm just going to draw in its modulus. So there's the modulus of Z2. Let's evaluate the modulus of that. So the modulus of Z2 would be the square root of minus 2 squared plus 1 squared, and that comes out as root 5. Okay, let us figure out what 3Z2 is. So 3Z2 is 3 times minus 2 plus 1i, which is minus 6 plus 3i, which I can write as minus 6, 3. And I'm going to plot that also on my argand diagram. So again, you can see that when I plot 3Z2, that it is actually 3 times as far away from the origin as the original Z2 complex number. But again, my direction has been preserved. So Z2 was up here in the second quadrant, if you like, with reference there to trig. And 3Z2 is in a straight line with it, and it's still in the second quadrant. Okay, so let's see what would happen now if I had minus 2Z2. So in this case, that would be minus 2 times minus 2 plus 1i. And that would work out as 4 minus 2i, which is the point 4 minus 2. So I'm going to plot that on my argand diagram. And you can see this time that I am now in a different quadrant. So what's after happening is, if you imagine that Z2 is going this direction from the origin, when I multiply by a negative, what I'm effectively doing is reversing my direction. So instead of going this way, I'm now going this way. And of course, because I'm multiplying by minus 2, not only am I reversing direction, but I'm going twice as far from the origin. Calculate the modulus of minus 2Z2 and compare it to the modulus of Z2. Pause the video and then check and see if you're correct. So the modulus of minus 2Z2 is the modulus of 4 minus 2i, which is equal to the square root of 4 squared plus minus 2 squared, which is root 20, which of course is equal to root 5. So when you look at the modulus of minus 2Z2, it's twice as big as the modulus of Z2. Notice that the modulus itself is always a positive number because it's a measurement of the distance from the origin. Also note that scalar multiples of my original complex number are always going to fall on the same line through the origin. To convince yourself of this, calculate minus 3Z2 and compare its location with the line that's been drawn already. Another word that we can use for scalar multiplication, or the effects, the visual effects of it is dilation. And we'll encounter this word again when we deal with enlargements in a later geometry chapter.